I want to talk again about linear regression, and I want to finish that topic off from last week. So let's first look at the things again we did last week. So first thing is, what's the first thing I usually do? I've got some files I want to work with. I want to do a scatter plot, and I then want to see some sort of prediction whether there's some sort of link between the variables. So where do I store that file? I'll store it somewhere on my hard disk. So usually the first thing you do is, so just a reminder, you set your working directory. So in this case, I've got my files, so this is BU1106, and I've got my stuff in a folder called Regression. Yeah, and I set that as my working directory. And here's the command. I could have also typed it in manually. Now, something I mentioned in the past is that usually we want the kind of things we do to be reproducible. I might want to run the same kind of commands again another time, so it's usually a good idea to put them all into a script file. In this case, I'll just copy and paste it. And that way I can save the script file, and down the line I can just run all those commands again. Let's say you work for a company after your studies, and they ask you to create some statistics based on some data they've collected. You might want to create some sort of graph, some sort of plot at that stage, and you can then of course save the picture. But maybe you want to recreate those statistics, and they are quite complex, so it's usually a good idea for you to store all those commands, and you can then save them as an R file. You just save this file with the file extension. Lecture 16. The convention is usually to use the file extension .r, uppercase R. And now I got it saved. And I could have 100 commands in there. I can just run them again another time. Okay. So let's have a look at the files in this folder. And if I click here on the Files tab, I'll see the files stored here. So I want to open that file again. That shows the absence of your group in the first semester's lectures and the grade you got for your first part of the assignment. And I stored them in this CSV file. So again, CSV is comma-separated values, or that's what it usually stood for. So we just dump all the values in there and we separate them with a comma. Let's have a look at that. But these days, we can also use other things, other symbols to separate the values. So, BU1106, regression. Yeah, and it's a CSV file, and because this is a Windows machine with Office installed, Windows suggests opening this file with Microsoft Excel. But then it will just look like any other spreadsheet. So instead I'll open it with a normal editor, and you can see here, look, we've got all the values. The first line in this case is some sort of label. Assignment 1, part 1 grade, and here absence for the lecture. And all those rows are different students basically. Yeah? So one of you didn't have any absence at all, so was present all the time, and has a grade of 60.4. Yeah, that's my internal grade. And in this case I coded it like this, that 0 is basically no absence at all, and 1 was representing 100% absence. So 18 would mean 18% absence. In the first semester, how many weeks did it have? I think 12, something like that. Yeah. So there wouldn't be a student with 17, because 17 isn't really a valid number. But here we've got 18, 45, 64, 9. So we've got 9, we've got 18. So maybe each class represented roughly 9% of your attendance. So if you missed 2 classes, you had 18% absence, something along those lines. Okay. So those CSV files, they're quite popular in computer science because they're easy to read with all sorts of programs. And they're much more popular for these kind of applications than an Excel spreadsheet, because Excel, there are new versions all the time, and the way they save the files is changing every now and then. Whereas this is so simple, so straightforward, we can always basically deal with these files. Okay, so I want to read this file, bu1106 grades.csv. Anybody remembers what the command is called to read a CSV file? It's quite straightforward. It was read.csv, and as usual, while I type it in, you see the yellow box popped up. At the bottom here it says press F1 for additional help. If I want to know more, I just press F1 and look here in the bottom right, the help page popped up. So when you do R tasks, it's usually very useful. You want to know more about the specific command, how to use it, you just press F1 and the help file will pop up. So I want to load my file. Let's go back here to the files folder. So it was called bu1106 grades.csv. We got that now. But if I just run this command now, where does the content go? Where does this data go? It just gets outputted to the screen. But we want to remember it, we want to work with it. So, what's the shortcut to get the last command up again? I'm too lazy to type it in. What do I press in RStudio? Yeah? Just cursor up. It's the same if you're in MS-DOS, or I think in MS-DOS. Certainly if you're on a Linux machine, cursor up usually brings you the last command back. Actually, you can even basically go through all the last commands. If I press 5 times cursor up, I basically get the 5th previous command. So that they're all stored there. So I said to typing again. So actually I want to put the whole thing into, let's call it bu1106. Okay. And I press enter, and it then should appear at the top right, in my environment, where I can have a little glimpse into all the data held in our memory. And here I can see here all the values. And just in case you've got an extremely good memory, last week there were 26 observations in here. When I looked at it again, I noticed that when I entered the data, there was one student who basically had had no grade. So it was a student who must have left. So we had a student who had an entry for absence, but who didn't have an entry for grade. And then that was coded as NA, a bit like not available. And when I then run the statistics as a test that I want to do today, or those kind of things, that caused some problems because the system didn't like NA values in there. So I got rid of that student. That student left the university. So now it's 25 observations. Okay. So I want to look into BU1106. What do I type? I want to see here on the console what's in BU1106.
Just BU1106.
Yeah, yay. Let's copy this over, I might want it later. So BU1106. Here it is. Yeah. And anybody remembers one of those commands from the data camp course you did, the first one, Introduction to R? There's a command that you can use and then it gives you some further information.
Summary?
Huh?
It's summary.
Summary is good, but it's not the one I was looking for. But let's try summary. Summary, BU1106. Oh, here we are. So now we get the mean, median, first quartile, third quartile, minimum, maximum, all those values for the grade and for the absence. And we looked at those, I think 2 weeks ago, was it? So median was one type of average, mean was another type of average, maximum value, third quartile. Remember when we were counting those blocks on the screen? Yeah. So some of these is a good one here. I want to draw a scatter plot of this data. Yeah, we looked at those last time. So the command to draw a scatter plot is plot, BU1106. Oh yeah, and again, you know, the moment I type plot, yeah, I can press F1 again. I get more help here. So it's BU1106. And here's our plot. Yeah. Which axis is the x-axis? Huh?
The horizontal.
Yeah, yeah, very good. And the other one is the y-axis. Okay. The names are not very good at the moment, so I want to rename my axis. What was the command? Stuff we've done a few times. Names. So I want new names for BU1106. So if I give new names, which one you think I hand over first? The x-axis or the y-axis? This one's straightforward. X, yeah, okay. So let's call X grades. And Y we call absence. But now I've got two values to hand over, so how do I combine? How do I concatenate those two values? What's the function? Something we use all the time. You're giving all the answers.
I know, you keep staring at me.
Everybody keeps staring at you for the answers. Okay, C. Okay, so grades. And then we got absence. Here we are. Okay. Still looks the same in the plot, but here we can see in our memory it already looks different. So I want to plot it again. I just place, arrow up twice, cursor up. Here we are, and here's our new plot with the new labels. The other thing I did a bit unfavorable was, I coded 100% as 1. So I want to change that. I want to code it in such a way that 100% abscess shows as 100. Yeah, then when we look at slope and so on and intercept, then the numbers look a bit nicer. So how do I change absence? Instead of 1 it should be 100. Instead of 0.5 it should say 50. So what do I do with the numbers on the y-axis? Anyone else? It does 2 again.
I think times by 100.
Times 100, okay. But I only want to multiply the y-axis with 100, and I want to multiply the base with 100. So how do I do that? BU1106. Now, which kind of brackets do I need? The squarely ones. Okay, yeah. BU1106 2 gives me the second column. Okay. BU1106, the second column should be the second column. Yeah, the new second column should be the old second column times 100. Yeah, and if you look here at the top now, things look different. We can plot it again. Let's plot it again. Plot. Yeah, now the picture here is updated as well. Okay. So this is this BU1106. We've now got a nice collection of numbers that I would like to keep. And because I think I'll mainly work with it in R, I want to just save it in R format. So, how do I do that? There's a command called, have a guess? Save. Yeah, and I can press F1 again for additional help. Writes an external representation of R objects to the specified file. Usually there are some examples at the bottom. And at the bottom, if you look, you see that actually, look, the file extension we seem to use seem to be R data. Yeah. So script files, like the one here at the top, where I store many commands, one after the other, we save those usually as .r. But objects like this, if I want to save those, I usually save them with .r data. Okay, I want to save BU1106. Let's have a look at those examples here. Let's see whether we can figure out how to do it. So what do I need to type? Yeah, let's try to copy that. In this case, it looks like they saved two things in that file. But how could it work saving BU1106? Yeah.
Just take BU1106.
Yeah. Okay, now it knows what we want to save, and now we need to say where we want to save it. So we need to give it a file name. So let's
Give me a comma there, something.
Yeah, and then here in this example it says file is, so let's try file is. Let's try that BU1106.r data. Let's have a look whether it's gonna work. It didn't complain, so it might have worked. Let's go back to Windows Explorer. Yeah, and here it is. Look, it's 1122. And this file was saved at 1122, so this is the one I just saved. Okay, that worked. Yay! Okay, let's go back to the plot. So, something we discussed last week. Does there seem to be a link between the grade and the absence? Who thinks there's a link between the grade and the absence? Hands up, who thinks there's a link? Okay, who thinks there's no link? It's a bit wishy-washy, you know, but to me it looks like there might be a link. Is the link positive or negative? You know, positive link would be higher x-axis is higher y-axis. So higher grade is higher absence. Is that a link? The other way around would be a negative link. Higher grade is lower absence. Positive or negative? Negative. Okay. let R draw a line. Or we can draw a line first. Yeah, you can save those files. Yeah, from here. Wait. But I'll just try the snippet tool. So, oh yeah, now I can draw on it, can I? So who wants to draw a line? Can I draw? Oh yeah. Who wants to try to draw a line? Any volunteers? Come on, I need somebody to come to me. You are coming to me, eh? Come, you draw a line. Looking away doesn't help, I picked you. Come, I volunteered you. Come. So, try to draw a line that you think represents what's going on. If it tries to create some sort of prediction of the model, yeah, how would we draw that line? You want the line to be basically as close to all the dots as possible. Okay, we can use my cardboard sleeve here as a ruler if you want. Or you can draw free-handed if you want. But we'll try to draw a line. Draw a line that is as close to all the dots as possible. A line that represents the link between grades and absence. We did it last week. Come. You need to go on this one. Okay, good. Thank you. Okay, that's our prediction. Are we happy with this prediction? Yeah, looks pretty good. Yeah, okay. Let's get, oh, where's my mouse? Yeah. Let's get R to draw the line and see whether it's very different. So, we did it last week, LM. We got a linear model. Now we specify basically the which axis. So we've got absence and grades, and the whole thing is from the file called BU1106. Okay. Remember intercept and gradient or slope? Yeah. So intercept was basically the line where the line at x-axis 0 hits the y-axis. Yeah. So we don't see a picture yet, but the computer thinks this line will hit x-axis point 0 at y-axis value 71. Yeah, so roughly here. Let's compare that. Well, this one's a bit higher. And the computer thinks, let's just go back. And the computer thinks the gradient will be minus 0.7. Yeah. So let's try it. Okay, the computer thinks the line starts somewhere at 71. Here's x-axis y, 71, and then minus 0.7. Yeah. So basically, for 1 unit we go right. We go 0.7 units down. So something roughly like that. Okay, let the computer draw it. Where did my mouse go? Okay. So the command here is a B line. And then I'm lazy. I can copy this all into a B line. Or actually, I'm even more lazy. Instead of having to type that all the time, let's put it into, let's store it away. Let's call it, yeah, let's call it model. Okay. So a B line for our model. And here's that line that the computer drew. Yeah. So it's quite similar to your line. The computer just starts a bit lower, but otherwise, very, very similar. Okay. So tell me in your own words, what does this line represent? This model that we created, is some sort of prediction of what the computer thinks is the relationship, of what the model thinks is the relationship between grades and absence. So let's say what's the minimum pass grade? 40. Okay. So let's look at this prediction. According to this prediction, according to this prediction, can I change color? That pen. So 40 is, let's use something as a ruler. What do I learn? You still have a set square here somewhere. Maybe this is long enough. Okay. 40%. Well, close enough. Let's pretend I hit 40. So what's the kind of absence we'd, let's say if we want to make sure we get 40%, what kind of absence can we, according to that model, get away with? What absence can we get away with based on, your group's grades for the first part of the first assignment? Let's try to figure that out, and I'll try to hold it as steady as I can. I'll use something else. This is too steady. Let's try this. Okay. Close enough. So, how much absence could we get away with?
40%.
Yeah. So 40% absence roughly is 60% attendance. So on average, kind of, or as part of the model, those of you who attended at least 60% of the lectures, usually passed. There are some exceptions. Yeah. So people. Yeah. All the people left of this line, let's change to another color. Yeah. Now all the people left of this line failed. And all the people under this line, so there's 3 students who actually had a lot of attendance, very few absence, but they still failed. But generally, it's true, but obviously this kind of model is not perfect. And I look at numbers next that help us determine how good the model is. There'll be numbers I look at, like standard of error and R squared, and this is some statistic. If you deal with physics or anything like that, you'll have usually much better predictions. But this is about humans, and trying to say your grade is dependent on your attendance in the lecture is a very simplistic view. What other things could influence your grade except the attendance of the lecture or the absence of the lecture?
How much work you do outside there?
How much work you do outside, yeah. What else?
Your intelligence.
Intelligence, yeah. Or how much you attended the practicals, yeah. That's not part of this at all. This is just about the lectures, not about the practicals. And even if you're intelligent, you know, somebody is more talented, maybe, you know, somebody might be great at accounting and bad at this kind of stuff, or somebody else, you know, might be good at, what else, you do marketing, you know, so we all have different talents. So it's a very simplistic view to basically try to predict, or to try to create a relationship between the grade and the attendance of the lecture. Nevertheless, there seems to be some sort of truth to it. And we'll have a closer look at those numbers next. Okay. Let's run summary over our model. And here we get all sorts of numbers. The most important thing here, let's not phrase it that way. One of the important things here is the significance. And the significance is quite high. So normally in statistics, we've got something we call the null hypothesis. NULL, null. Null hypothesis usually, for the null hypothesis we usually say the null hypothesis is there's no link between the two variables we look at. So the null hypothesis in this case is there is no link between the grades you get and the attendance or the absence of the lecture. And I phrase it very colloquially now. Yeah, so some statisticians, they might probably fall off their chair if I say it like that. But usually we want to be 95% sure. If we are not if the statistics don't say we are 95% sure about this, then we think it might have happened randomly. 50%, if the statistics says there's a 50% chance of this happening, are not good enough. If you run all sorts of possible scenarios, and in 50% it's like this, 50% it's like that, it was probably random. But if we are 95% sure or more sure, then usually we reject the null hypothesis. So if we reject the null hypothesis, we say there is actually a link. And the important number here is p. So it's all about the 5%. And in terms of p, this 5% is expressed as 0.05. Yeah? 1 would be 100. 0 would be nothing. 0.05 is this 5%. And here we see this number is lower than 0.05%. Or statisticians might say 0.05. They leave out the 0 before the decimal point. And here we even get 2 stars because, you know, it's not only good enough at this 5% border, it's even better than that 1% border. Usually after that, if it's, you know, if we cross that 5% line, the next point where we get excited is 1%. And then the next point we get excited is 0.1%. So this is, much less than 5%, it's actually 0.3%. So again, statisticians might fall off their chairs, but we are only 0.3% unsure about this. So we are 99.7% sure that there is actually a link. But just because we are sure there's a link doesn't mean that one of those variables completely explains the other variable. So we are sure there is a link between them, but we can also see that absence alone isn't everything. There are other things that must go and explain the grade. And this is where R squared comes in, which is that number here. And then we also got S value, the standard error. So R squared is basically how much can we explain. Yeah. So 0% would be that this model explains nothing. 100% would be this model explains everything. In our case, the number is 32%. So basically, we can say absence explains 32%. Absence in the lectures explains 32% of your grades. Yeah. So whether you attended the lecture or not, that's 32% of your grade sorted. I'm sure another big chunk, if we run statistics, would be how much did you attend the workshops. And then I didn't collect that number at all, but if I'd ask you how many hours did you learn at home, that would also make a difference. Usually, people say if you deal with human behavior, it's uncommon to get over 50% with R squared. So 32% is quite a good number. The other problem, of course, is if I start asking you, because absence I could measure easily. If I start asking you how many hours did you work at home, I don't know whether I get a good number from you, because it wasn't measured objectively. You might remember wrong. You might try to look better than you were by giving a higher number, or you might try to do the opposite. You might try to lower your number on purpose. Plus, if you set an hour in front of your book, but you were answering Facebook messages 10 times in between, is that still an hour, or how many minutes would you deduct? So if human behavior is involved, things can often be quite difficult to measure. But we know there's definitely a link. So there's still a 0.3% chance that this happened randomly and there is no link. Yeah, those things happen. There's a great web page. I'll have a look whether I can find it. I should have looked earlier. I think it's something called like strange correlations or something like that. Here. Yeah. Yeah. So imagine you got all the data. In the UK we've got the Office of National Statistics. In the United States they also got some different sources of data. In this case, US Office of Management and Budget and Center for Disease Control and Prevention. So basically people just took a computer and they fitted in all the numbers they could find, and they were looking for things that link together. Yeah. So in this case it looks like there's a strong link between US spending on science, space and technology and suicides by hanging, strangulation and suffocation. Yeah. Correlation 99.8%. But this is not the kind of stuff you can normally do. You see, number of people who drown by falling into a pool compared to films Nicolas Cage appears in. So it looks like the more movies Nicolas Cage makes, the more people drown in their pool. Yeah, 2007 we had a high number for both. 2003 we had a low number for both. Cheese consumption versus people who died becoming tangled in their bed cheese. Divorce rate in Maine versus per capita consumption of margarine. Yeah, it always looks like there is some sort of link, but actually, you can't go around combining numbers and then looking for a link afterwards. Yeah, you need to have a null hypothesis first. You need to have two variables where you think there might be a link, and then you try to explain it. And you know, if you look at if you compare millions of data sets, you know, like, I don't know, divorce rate in Maine versus, you know, movies, all the famous actors in the world ever appeared in, or whatever it might be, you're bound to find something. Yeah. And here the statistics always say there's a small chance that this happened by accident, by coincidence. But of course, you know, in this case we were looking for these kind of things on purpose. But this is not how science works. This is not how proper science works. Maybe, I don't know, some companies trying to sell you products, they would misuse it. But if you do it scientifically, you have two variables you want to look at, two types of observations. You start with your null hypothesis, you then compare. And in that case, we then get a good idea. In this case, we are quite sure that this didn't happen by coincidence. And our statistics tell us basically 30%, sorry, here we are, 32% is explained, of the grade is explained by the absence. Then we've got the standard error. So to look into that, I want to go back to a question asked a few minutes ago. What does this line actually represent? So this is some sort of prediction. With this kind of grade, what kind of absence would we expect? Or you can also look at it the other way around. So, how do we get to create that line? We actually just try to create a line that is as close to all the dots as possible. Yeah. And how do we measure that? We can measure the distance of each dot to the line. If there's a function called predict, and it basically gives me, did I call it model? I think I called it model. Yeah. Now this is not sorted by value. I think it's probably sorted by surname. So whoever was the first student in my list, now we predict a number of 27.7 for that student. For the second student, we predict a number of 16.63. And you can see we have certain numbers that will repeat. So let's look for repeating numbers. Yeah, for example, here student 11, we predict 71.36. Student 16, we predict 71.36. Yeah, because they had the same absence. Let's store the whole thing in predicted. So let's look at which student. Give me a random number between 1 and 25. Let's look at the first student then. Okay, so the first student we predicted 27.75.
Is that absence or grade?
Absence. Yeah, it's absence. Because the y-axis is absence. Yeah, it's absence. BU 1106. Yeah. Okay, so they didn't have any absence. Let's try another student. Let's try the second student. Yeah. Absence was 18, but we predicted 16.63. So what we can basically do is we can draw lines. And who went as far as the loops in our explanatory course? Yeah. So what's a loop? A loop is basically where we run the same code again and again, but yeah, we can input a different variable in there. Yeah. So in this case, I want to write the code that will draw lines between our dots that represent the students and the prediction. So we do it for student 1 to 25. And I want to draw lines, so the command is called lines. And now I need to give it the x and the y coordinates for the point of origin and for the point where I want to go to. So let's say in this case, I want to draw a line from the xy coordinates here, the student's grade and absence, to the student's basically position here with the predicted absence. Because this is linked to another number we calculate. So first, I feed the x-axis in. You will know 6 grades I. 6 grades I. Okay. And now the y-axis B1106. Absence y predicted right y, and then I can specify what color I want. Let's do it in that. Let's hope I didn't make a mistake with the brackets. Unexpected comma, okay, lines. Yeah. I opened, I closed the brackets here. Okay. Let's put the whole thing at the top. Then it's easier to check. So. Predicted. Yeah, now the second time I hit enter, I forgot about the loop because it was in a different line. Yeah. Okay. So now we drew all those lines here between the actual case that we have and the predicted number. So how did we create that line? We basically, our predicted line, we want the distance to the points as small as possible. So we basically draw the line where the red lines are as short as possible. And the computer thinks with this kind of solution, the red lines, they're very, very short. So we can actually, here we looked at absence and predicted lines earlier. 1106 absence minus sorry?
B1106.
B1106, thank you. Absence minus predicted. Yeah. So these are basically the length of all the red lines, and if I add them all up, 1106. Absence minus predicted. Yeah, the number is very small. Yeah, E minus 13 basically means, yeah, let's do a calculator.